Hello, everyone. My name is Shruti. I'm one of a product manager for Azure Managed Redis. And today we'll talk about how Azure Managed Redis is the new age Redis, Managed Redis on Azure, and how it helps with building AI apps at the internet scale. So most of you must be familiar with Redis. It has been around for a long time. You have probably using it already for your session store, for leaderboard, for reducing database cost or making your databases more performant. As Redis use cases have recently expanded along with the internet scale, right? It started out with some basic traditional scenarios, but Redis now has many more use cases that it can support, like time series, vector searches, JSON data, semantic caching. Times have changed, the internet scale has changed, and so has the Redis use cases have expanded as well. So today we'll be quickly covering what's new with Redis, especially the Azure Managed Redis. Azure Managed Redis is a fully managed in-memory data store on Azure. It's a first-party offering on Azure, and it's based on the Redis Enterprise software, which offers a much more cost-effective TCO compared to the Azure Cache for Redis offering, and it's also much more performant. It's up to 15% more, 15 times, sorry, not 15%, 15 times much more performant than the Azure Cache for Redis offerings. It is zone redundant by default. It has 4 nines offering by default, and obviously you can also set it up with a 5 nines setup with a geo replication, which will give you the 5 nines of availability SLA. As with the Redis software, it can support your accelerations scenarios for your applications. You can use Redis as a distributed cache. You can use it for session management. You can use it for leaderboards, PubSub, you name it. There's like so many scenarios where you can use Redis. But alongside those, Azure Managed Redis is also able to power your RAG scenarios, and you can also use it as a lightweight vector data store as well. How is that possible? So we'll talk about the secret sauce a little bit. How does Azure Managed Redis do that? But first, let's look at the state of AI agents today. Right. So AI agents today, this is a very simple depiction, but there's an input that usually a user provides, or there's some triggers or events that trigger the AI agent. And internally, the AI agent is essentially a bunch of instructions, a model, and a lot of tool calls that enrich what the agent can do. And then obviously it produces some kind of output that makes it productive. But if you look at the tool calls that the agent needs to enrich itself, it needs knowledge that's specific to your domain. It needs to be able to execute some actions so that it's more impactful. And then obviously it needs memory as well. So this is a high-level overview of what actually an agent looks like. But if you start doing agents in production, a lot of challenges start coming up, right? Gartner predicts that 40% of enterprise applications will have specific AI agents by the year 2026. So this is already up from 2025, where 2025 didn't have a lot of AI-specific task-specific agents, and that number is growing up definitely this year, and it will continue next year as well. But once you start putting AI agents in production, there's some challenges that are going to show up, right? Like the pace of innovation in the AI world is tremendous. How do you keep up with the pace? How do you keep yourself abreast with the new innovations, the new things that are happening in vector search? How do you use, or how do you adopt those things for your production scenarios? So that's one challenge. The other one is unpredictable cost. A lot of this is some is new for most of us. The way tokens work, the way tokens correlate to the dollar amount that you end up paying. A lot of times you will see you get surprises at the end of the month when you see your bill. So there's unpredictable costs in there. Model calls are expensive, and they take a lot of time as well. So there's this cost aspect as well that's quite challenging. And these agents, as we just saw in the previous screen, Agents need context and agents need memory to be more impactful. Once you solve all of these challenges, that's when you will be able to build enterprise-ready internet-scale AI agents. So today we'll be mostly covering these two challenges, right? The cost management and context and memory. How do you solve these two challenges with Azure Managed Redis? So I have my friends Phil and Roy who will join a little bit later, who will talk about these challenges one by one. So how does Azure Managed Redis do that? So the secret sauce is the Redis Search module that comes in that you can configure at no extra cost. So the Redis Search module allows Azure Managed Redis to do vector similarity search on embeddings that you store inside of Redis. So once you configure this module, it allows you to do similarity search or vectors on vectors, and that powers both the cost savings and the memory context scenarios that I just mentioned. Now that I've given up the secret sauce, I think it's time for me to take a back seat and let Phil and Roy later on show you all the magic and how it happens. So this was it. From my side, take it over, Phil.
Hi everyone, my name is Philip Laussermair. I'm a Senior Solutions Architect at Redis, and I specialize in Azure Managed Redis. As Shruti mentioned, I'm really excited to walk you through one of our top AI use cases, semantic caching, and it's all powered by our semantic search capability in Redis Search. So if you know Redis, you probably think of caching, right? This is one of our bread and butter use cases. This is what we actually were founded on. And for the last 10 years or so, this is really what we focused on. And the typical pattern, you'll see it here. It's, you put it in front of a database. It's meant to offload a lot of repetitive costs, take off pressure from the database, improve performance. And that's, the typical pattern. You check the cache if the existing key is already in there. If it is, you serve it to the customer. If not, you call the database and then load it back into your Redis instance. So this works extremely well. It's in any best practice with databases, you'll probably see caching come up as one of the first ways to optimize and improve. But a lot of things, as Shri has mentioned, has changed in the last decade or so, especially in the last, let's say 2 or 3 years with the advent of generative AI. So at Redis, what we've been able to do is exact key value match caching is not ideal for LLMs, right? I could ask a query that, Shruti could send in a few minutes later in a slightly different variation, but it could be the same underlying intent, right? It could have the same meaning. And in that scenario, tokens are expensive. You're going to generate a full amount of tokens for a scenario where you potentially could have saved on that. And that's where semantic caching comes into play. So the general idea stays the same, right? We're going to check Redis, see if there's a cache hit. If not, instead of calling a database, we're going to call an LLM. But really how this is all being powered is now you can store your vector embeddings in your Redis instance. And then using vector similarity search, as prompts come in, we can then check the cache, compare the similarity, and based on a threshold that you would set, that determines if it was similar enough to be a cache hit or not. And we actually have a demo, so I can show you this live, what this would look like, how it would be for you or your customers. But at the end of the day, the idea is this is really meant to save on tokens, which we all see in the news, day in and day out. Token cost is exploding. Response time, of course, is a huge performance factor. The agents are running longer and longer. They're getting much more intelligent, but that could lead to seconds or even minutes of wait time. And then finally, consistency, right? There's certain use cases where you sometimes don't want an LLM to be so non-deterministic, right? If you're going to ask it the same prompt or the same underlying intent every time, you want to be able to have a sense of confidence that you're promoting the same answer that you intend, right? So it gives you some confidence from that angle as well. But now that we have a general understanding of the underlying architecture, why don't we jump into a demo? And that should make it a lot more clear and pretty exciting. Okay, so now we're in our semantic caching demo here. So just to orient you, I want to show you what you're looking at here. On the left side, I want you to think of just a regular LLM, take, Copilot, ChatGPT, Claude. That's the left side. The right side is the same idea, but with semantic caching underneath the hood, powered by a Azure Managed Redis instance live as we go along. I want to point out a few other items, some metrics down here that will capture every time we send a prompt. But really, without further ado, we can jump right in. So let's say we were going to send a prompt, how do I improve product search relevance using vector embeddings, right? Let's pretend we're an e-commerce company, Contoso, and this might be a typical question that would be asked. So what's happening right now is both are acting like a typical LLM. I sent a query, we're going to get a response. They were two separate responses, right? So generative AI being non-deterministic, you can see the same query at relatively the same exact moment gave me similar but a little different answers, right? The one on the left took 118 tokens, the one on the right 131, and both were roughly between 1 to 2 seconds in timing, right? So now let's take a similar phrased search, but not exactly the same value, right? So instead of how do I improve product search relevance using vector embeddings, let's just change it up. How can vector embeddings make product search more relevant? And what I want you to take focus on is right there on the right. What you saw was a semantic cache hit, right? So the first thing you noticed was it was extremely fast. The second thing you'll notice is it is the exact same response, right? So we're taking advantage of that previous response. And so no tokens were generated. That's one of the biggest things to highlight. On the left here, since this was just our normal LLM call, every time we send a request, we're going to get a response. It did go and generate another 126 tokens. As you can see, very similar, but for this kind of query, we didn't get to take advantage of the previous one. So every time it's just going to make net new calls. So I want to show you one other thing. If I click here on this query, these are the steps that actually happened underneath the hood in that, almost millisecond it took to get the response back. So the first few things, first off, of course, we're going to check the cache. There's different ways you can optimize semantic caching. The first one being we actually can do an exact cache lookup. So if it was a key value pair, we could take advantage of that and actually just serve it like a data cache would. Since that didn't exist, we then went and generated our embeddings. We got our embeddings back and did the vector similarity search. We, based on our threshold, the cosine similarity was high enough that it triggered a cache hit. And so that's what you saw as the end user, right? You got that result super fast with no tokens being spent. So just to show you what it would look like, again, in the same scenario with another query, not related to any of these, if I fired off, both are going to act just like typical LLMs, respond. The reason I highlight that is, this is all running every single time underneath the hood. Because Redis is an in-memory database, it's lightning fast. So, just because this is happening, customers aren't sitting around waiting. If I throw in, more, you'll see you wouldn't notice it was running any other time, right? So next I want to show some more deep dives on vector similarity search, right? So taking our first prompt, let's see, what's the most cost-effective caching strategy for serving personalized product recommendations to 10 million daily active users, right? Then we have a few variations below that are either extremely similar or even unrelated, right? So what I'm going to do is I'm just going to run a test that is generating the similarity using a cosine vector similarity search. And this similarity threshold here is what you would set in your application or client, right? That's the threshold that you are comfortable with for what would trigger a semantic cache hit or not, right? So just here, what we generated at a 50% similarity threshold, it would need to clear. We can see that these top 4 prompts would be considered a semantic cache hit. If we wanted to increase that, right? Let's say we wanted to go to 75%. The first thing you notice is this variation 4. It's no longer considered similar enough to do a semantic cache hit. I should call out this first one, prompt hash hit. This is that exact same key value pair, right? So this is going to be a match 100% of the time because it's an exact key value pair. And finally, right, if we wanted to be super strict and went all the way up to 90%, every single one of these would be a miss, right? So that gives you the flexibility of how strict you want each threshold or each scenario to be with your threshold using vector similarity search. Finally, I want to show you another scenario of what it looks like for your end users that are being powered by the same managed Redis instance, where you might be thinking, okay, this is great. I love these semantic cache hits, saves a lot of tokens, but how do I ensure no data leakage, right? If someone asks a very similar question, but they have specific data to them that the LLM is using, how do I make sure that's not being shown to anyone else, right? So we have our two users here, merchandiser Mia and platform Priya, and they have different roles in Contoso. And what we're going to do is we're just going to ask, based on some memory we have on the users, what is your role, right? So on the left, merchandiser Mia, on the right, platform Priya, and I'm going to show you again, first LLM call, nothing there. Let's say, what's my job, right? If I send that one, what you're going to notice is each got a semantic cache hit, but strictly on the keys we have saved for them, right? And how that's being done is, in the way you structure your keys in Redis, you would actually set up the naming convention specific to each user or domain or whatever fits your use case. And the search engine can, be queried based on that formula, essentially. So in this example, right, we want to make sure that it's in a per user format so that there's no chance of leakage. On the flip side, right, there are cases where you actually want a global cache. And that one would be something like a FAQ bot, right? Where, it doesn't matter who the user is, they're all going to be asking similar questions, and you really want to take advantage of those. So let's pretend this is our FAQ bot on our Contoso website that unauthenticated users can come and use. So let's start with the first one, right? What are your hours? And these are, semantically different. This one was considered a cache hit because it was similar enough to this. This is just a vanilla LLM, so it doesn't have hours. But you can start to see, right, where in these public instances, you can generate a lot of semantic cache hits and save a lot of tokens, right? If this visitor B was a user that was coming in, say, 5 minutes later, they wouldn't know any different based on these responses, obviously using real company data. But in that scenario, almost every response in this chain would be a semantic cache hit, and there would be no tokens spent in that scenario. So again, one of the benefits and the flexibility of either a global or per user cache. Finally, just to wrap up, I want to give you a sense of what does this look like at scale, right? So a quick calculator of what this looks like in an enterprise use case. Let's even drop this down to say 200,000 daily queries, a 70% semantic cache hit rate, extremely low on the token sort of budget in this scenario, and the pricing of GPT-5. So in this scenario, in an annualized basis, that would be just about $300,000 a year for your token spend. And the way to think about the savings with semantic caching is whatever your cache hit rate percentage is, that is your net savings, right? So with a 70% cache hit rate, we're going to get 70% savings off of this overall spend. And so what that comes out to is just under 100,000, around 90K a year. This also factors in both the embedding costs that you would have to pay for each query and the actual Redis instance that could power a load like this, right? And as you can see, even factoring those in over an annualized basis, that would save over $200,000, right? The last thing before I wrap up is I want to call out this break-even rate. This is the number of semantic cache hits that you would need to have in your setup for this to be break-even. So what this is saying, at a 1.2% cache hit rate, you only need 1 out of 100 queries in your setup to be a semantic cache hit for this to ultimately save you any money net after that first query, right? So again, it's very scalable. It's once you set it in place, you can kind of legal in there. It really helps with performance. It helps with token spend. But overall, that is semantic caching with Azure Managed Redis. And now I am happy to pass it over to 𝗦𝗲𝘀, who's going to talk a little bit about how you can use Azure Managed Redis for agent memory at the same time. Thanks, everyone.
Thank you, Phil, and also Shruti, thank you for the great presentation and the demo and everything that we saw. So I'm Roy, based out of the Netherlands. I'm a solution architect for Azure Managed Redis, covering EMEA and working with customers and partners to make them successful when they are adopting Azure Managed Redis. I'm going to talk a little bit about agent memory. I'm just going to explain why that is important and how you can use AMR for that. And then I will jump into a quick demo as well to showcase that. So when we think about an agentic workflow or an agentic AI system, we're thinking about different agents working together to have make it sure that you have high fulfilling AI tasks. But those agents can act even better when you're thinking about when they can leverage memory as well. The way we determine this is that we have the short-term memory and the long-term memory. So for short-term memory, we often think about the interaction, the conversation, a certain state and stuff like that, that we are saving within that short-term memory capability, right? But then if you look at the long-term memory, we think about from a personalization perspective. When a user is interacting with the AI system, you basically want the AI system to be aware, what are the preferences? What is some of the things that are important for this specific user? Or what is something of their interest and stuff like that? And you can go nuts with this, right? The world's your oyster if you think about it. So what we are doing is splitting those two out, more on the conversation, history, estate aspect, and also the preferences, the behavior, the durable facts, and the interest for a real personalization type of interaction. Now, when you think about this and a user is interacting with your systems, now the agents can have rapidly fast access to that data. And they can use that when they are determining, they're using specific tools, they're using an LLM to do certain reasoning about it, whatever you have built, but they can rapidly fast get that data and include that within the whole pattern that they are doing. And this is where Azure Managed Redis really, really shines if you are saving that specific data into AMR. And also think about when agents are working together and specific agents wants to give context to the other agent, it's stored within AMR. So it can just easily say like, hey, have a look at this. And now the new agent that needs to do something else within the agentic workflow, they can grab that information as well, giving you a way better experience as a user, but also allowing you to interact better with your consumers and your users, right? So I do have a small demo around this. So I'm going to hop over to another screen. Just give me 1 sec real quick. So here you can see the demo that we have built. So basically it's the same context of the previous demo that you have seen by Phil. So on the left-hand side, you see the without memory capabilities, and on the right-hand side, you see the with memory capabilities. So this is everything around personalization, and that's how we have built this. So this is basically an AI system where I can interact with the system, and the system knows about me. It has stored the conversations that we had, and it has stored the durable facts, the preferences, what type of work do I do, right? So in this scenario, let me hop over to myself, and let me just basically teach the AI a little bit about me. So I'm going to say, hey, I'm a software engineer working on machine learning projects, and I love hiking photography on the weekends. So when I'm going to send that to both, you're going to see on the left-hand side, it's going to respond like, hey, nice to meet you, great, but nothing is being saved. Not on the conversational side, not on the long-term memory side. On the right-hand side, you actually see that we are analyzing the message. We can give a response back, and we're going to remember certain facts about this user. In this case, this is me. So the user is a software engineer, and it loves hiking, and it loves photography. And if we actually look to the agent activity log, it runs through a specific aspect of things to do to analyze the message, reason about the message, and also saving the aspects that we want to save to the long-term memory. So now, because we have stored the long-term memory facts as in a vector database, as a hash vector, I can also use semantic search, which my colleague was talking about before, to ask questions about it. So if I'm going to say, hey, what do you know about my work? It's probably going to give me a response back. This is what I know. You like working on machine learning projects. Your main stack is this and this and this. So it actually knows what I'm all about. And if I can ask it, hey, what activities do I enjoy? It's going to give a reason back as well. And you see on the left-hand side, it doesn't have a clue. This AI system doesn't know. But on the right-hand side, because we have that long-term memory in place, it actually knows about me. What we have also done in this specific scenario is we set TTLs, time to live, on the specific short-term and long-term memory. So the short-term memory is only kept for 30 days. And every single conversation I have with this specific AI system is going to be saved for 30 days, right? So I can jump to another one, right? Or I can jump to, I also like sim racing and stuff like that. Now, the long term, we're going to save that a little bit longer, over a year. Because I can be a user and I can go away for 2 months, but the moment I'm going to come back and interacting with the system, I want the system to know about me. So basically, how does this work, right? And I'm going to jump to how it all works. So basically, you send a message, what are my hobbies? This generates a query embedding because when we're using the text embeddings 3 small model from Azure OpenAI for this, it's going to do a vector search around this. It's going to build some context, and we're using AI to generate a response as well. Any new facts will be saved as vectors, and we update the conversational history. So we're all working together basically and have a whole different flow on this specific system. Now, if we go to the long-term memory, this is actually super interesting. So what we are saying over here is, hey, we want to save any personal information, any work, any preferences, and any interest. But we don't want to save every single thing. So we are going to give the AI system or the different agents, we're going to give them a set of instructions. And then every message that I'm going to send, the agent and the AI system is going to analyze it. Is this a permanent fact or is it temporary? So if I'm going to say I'm feeling tired today, that's not going to be saved as a long-term memory because it's a temporary thing. I can feel fine tomorrow, right? Or would this help me in personalizing future conversation? Is the fact about the user and not about the world? Then we're using a special tag if we want to save that. And we have the specific decision criteria and it's going to save it or skip it specifically, right? So in this specific scenario that I also showcased, hey, I'm a software developer at Microsoft and I love playing tennis on the weekends, right? It's a little bit different than the one I showed, but it's roughly the same. We are basically identifying multiple facts and we're going to store those facts in the vector database while using an embeddings model to create embeddings and then store them, obviously. So we're using vector hash for all these different type of facts, right? So that's very, very interesting. Now, let me jump to this one. How would this potentially look like from a AMR storage perspective? So as you can see over here, we have the short-term memory. We have Phil talking to the AI system. You have me and Thomas talking to the AI system. And you see the TTL standing there as well. And I can actually click this open. And this is basically the whole conversation that we potentially had. But then if I go to the vector facts, you see these are all the facts that we have stored. Interest, personal, work. And we tag them as well. So this allows you to give multiple agents access to durable information or to the short-term information rapidly quick. And now think about it, if you have multiple agents working together, they all have that same information and they can access that rapidly quick, increasing the performance of your whole workflow and therefore giving your customers a way better experience. If you think about a travel companion type of application, right? This travel companion knows that I like Airbnbs and early flights, and I don't need to specify that every single time I'm interacting with it. So every single time I'm talking to the system and it's helping me to book my travel, it already knows this. And it gives me a way better experience. And I get, as a user, to a faster result that I'm looking for, booking my flight without telling it every single thing. The agent memory capability of AMR also fully integrates with the agent framework, the Microsoft Agent Framework. So there's also something that is natively embedded and supported around that as well. So that was my quick demo around this and why I think agent memory and using AMR for agent memory is a very interesting way of giving your agents that specific information that they need to have those high fulfilling AI tasks. So thanks everyone for listening to us and learning about semantic caching, semantic search, agent memory, and Azure Managed Redis as the foundation for all of that. I want to say a big thanks to Phil and Shruti for doing this together with me. If you have any questions, any feedback, any comments, or anything at all, feel free to send us an email. We also have some resources that could be very useful, and we have some different samples of the demos on GitHub as well. So thank you very much, and if there's anything, feel free to contact us.